This video is part number 2 of my galvanic cell series, where I'm going to cover an overview of cell notation, cell equations, and cell potential. So let's start with cell notation, and let's first look at a zinc-copper galvanic cell. So this is where zinc oxidizes, so it loses electrons, and copper 2+ is accepting electrons or reducing. Now, if I had to draw this out every time I wanted to represent this cell, that would be very time consuming. So what I can do is use something called cell notation, which is just a shorthand representation for what's happening inside a galvanic cell. And to write this, we need to know 4 things. So let's go through what each of these 4 things are and identify them for the cell. So first, what's oxidizing? As mentioned before, oxidizing is when you lose electrons. So we can see here that zinc solid is giving up 2 electrons. So that means zinc solid is what's oxidizing. And then the product of oxidization is basically just what zinc solid turns into. Or another way to think about it is what we end up with. And that's zinc 2+. And then we have what's reducing. So that's copper 2+, because that is gaining electrons, and reduction is the gain of electrons. And then the product of reduction, or what we end up with in this reaction, is copper solid. So after we have these 4 things, all we need to do is put a straight line between zinc and zinc 2+, and copper 2+ and copper. And you can kind of think of this straight line as the reaction arrow, if that helps you remember. And then we add a double line between the zinc side and the copper side. And you can kind of view this as the physical separation between these 2 half cells. So that's it. That's how you would write this using cell notation. So to summarize, you can tell what the reaction is by looking at this notation, because we have zinc solid turning into zinc 2+, and then copper 2+ is turning into copper. And this is why we have these 2 half equations above, so they should match up. And more scientifically, this is what we call each of these substances. So the reductant is basically what's oxidizing. The conjugate oxidant is the product of oxidization. The oxidant is just what's reducing. And the conjugate reductant is just the product of reduction. Now, I just want to touch on something called conjugate redox pairs. Now, what this means is basically 2 substances that differ in the number of electrons. So you can see in this case, we have zinc 2+ and zinc solid. And that's one pair, so that's one conjugate redox pair, because they are both zinc, but one has less electrons than the other. And the other one is copper 2+ and copper, which is another pair because they are both copper, but they only differ in the number of electrons that they have. So you can see that each half cell, or each half of our notation, contains a conjugate redox pair. So that's another way to help you remember our cell notation. Okay, following nicely from this, let's try and find the full equation for this reaction. So these were the 2 reactions that we just had, but I've just highlighted them on the electrochemical series for your reference. And the way we find our full equation is first making sure that our reactions are going the right way. So you can remember that top left always reacts with bottom right. Or another way you can do it is to draw a backwards Z and put arrows on the end, which will tell you which way the reaction is going. Then we rewrite the equations so that the arrows are pointing the same way. This isn't necessary, but it does make it easier to see. And then finally, we just add the right-hand side and the left-hand side, like this. And then what you'll notice is that on both sides, we have 2 electrons, and that means they cancel out. And so we get our final full equation looking like this. Great, now let's look at another example. So using the same steps as before, top left reacts with bottom right, we get the following 2 equations. But if we just add them now, you can see that the electrons won't cancel out because we have 2 electrons on one side and 3 electrons on the other. And this is important to note because our full equation never has any electrons in it. Only half equations contain electrons. So that means to get our full equation, we need to multiply both equations by a certain number so that the electrons cancel out. One way to do so is we can multiply the first equation by the number of electrons in the second, which is 3. We multiply the first equation by 3. And for our second equation, we multiply it by the number of electrons in our first equation, which is 2. So we multiply the second equation by 2. So to summarize, we're basically multiplying the equations by the number of electrons in the other equation. And what this does is it helps you get the same number of electrons on both sides. So you can see that we now have 6 electrons on both sides, so we can add up the equations like we did before. And you can see the electrons cancel out, and we get our full equation like this. Now that we know how to find the full equation, it's often useful to also find the cell potential. Now, cell potential goes by a couple of names. So you might see it as EMF or electromotive force, or you might see it as this letter that looks like a curly E, and it's called epsilon, and that is the symbol for cell notation. To understand what cell potential means, let's look at this snippet of the electrochemical series, and let's go through what the values on the right column mean. So these values, the 0.34 and the minus 0.76, these are the standard electropotentials for these half cells, measured in volts. And what electrode potential means is it's basically how much a substance wants electrons. So if there is a higher electrode potential, that means this substance really wants to gain electrons. And if something has a low electrode potential, that means this substance does not want to gain electrons, or in other words, it wants to release electrons. So we can see for the copper reaction, it has a higher electrode potential than the zinc reaction, which means that copper 2+ wants to gain electrons. And that makes sense because we know that copper 2+ in this cell is what reduces. And likewise for zinc, it has a lower electrode potential, so it doesn't want electrons as much. And that's why zinc solid is giving away electrons. So now that we know what electrode potential is, cell potential is just the difference between these two electrode potentials. We take the higher electrode potential and minus the lower electrode potential. So cell potential and electrode potential are not the same thing. However, the units are also in volts. So the cell potential, which is just the difference in electrode potentials, tells you the galvanic cell's ability to push electrons around the circuit. Which means that if we have a large difference, one reactant really wants to gain electrons and the other one really wants to lose electrons. So there is a greater push or energy on the electrons. So this is why when choosing batteries, we usually want to choose 2 half-cell reactions that will give us a relatively high cell potential, because that means we have a higher voltage for our battery. So to calculate this, it's fairly straightforward. We take the electrode potential of the higher reaction, so copper in this case, and we minus the electrode potential of the lower reaction. So it's 0.34 minus, and then in brackets, negative 0.76. So make sure you have that bracket there. And this will get you 1.1 volts. And just a heads up, the cell potential, or EMF, should always be positive in a galvanic cell. So if you got a negative as your answer, just double check that you have the brackets or the correct orientation for your reactions. So that's it for this video. Here's a summary if you want to pause or screenshot. But anyways, for more explanations on galvanic cells, check the links below to see these topics that you see on your screen explained in more detail.